Strip away everything, and a neural network is just matrix multiplication, repeated billions of times. So the entire question of AI hardware collapses to one thing: which chip multiplies matrices fastest? The answer is a story of escalating specialization. The CPU can do anything, but not quickly. The GPU stumbled into massive parallelism almost by accident, and the TPU was built from scratch for neural networks alone. Each one trades flexibility for raw speed on a single operation. Start with the CPU, it computes a result fast, then sits and waits for the next piece of data to crawl in from memory. Compute, wait, compute, wait. That gap between fast arithmetic and slow memory is the von Neumann bottleneck, and the processor spends more time waiting than working. CPUs fight it with deep pipelines, branch predictors, and layers of cache. All brilliant machinery, all aimed at flexibility and feeding a few complex cores. But neural networks don't want clever cores, they want many simple multipliers all firing at once. So the GPU made a bet: throw out the branch predictors and the complex control logic, and fill that silicon with thousands of simple arithmetic units, 2.5 to over 5,000 of them, all working at the same time. It was designed for graphics, run the same shading calculation across millions of pixels, and a matrix multiply has the exact same shape, millions of independent multiply accumulate operations. The fit was almost perfect. The bottleneck isn't gone though, just reduced. Moving data is still costly even inside the GPU. Zoom into a GPU and you find a hierarchy. The whole chip, divided into clusters, divided into streaming multiprocessors, SMs, each packed with cores. Inside one SM, CUDA cores, the basic units doing one float operation per cycle, tensor cores for small matrix multiplies, special function units for things like sine and exponentials, and registers and shared memory, the fastest storage on the chip. To put numbers on it, an nvidia H100 has 132 SMs, around 16,900 CUDA cores, 528 tensor cores, and 80 gigabytes of memory. How do you program thousands of cores in a hierarchy? A thread runs one copy of your function on its own slice of data. Threads group into blocks up to 1024 that share fast memory. Blocks form a grid covering the whole problem. But the real execution unit is the warp. 32 threads that all run the same instruction at the same moment on different data, that's SIMT. The danger is an if statement that splits the warp divergence, where half the threads run one path while the other half sits idle, then they swap. Wasted parallelism. But neural networks barely branch, so their warps stay convergent and no lanes go to waste. One operation dominates everything: GEMM, the general matrix multiply. Accelerate it and you accelerate all of AI. A CUDA core does one floating point operation per cycle. A tensor core does an entire small matrix multiply and accumulate, D equals A times B plus C, in a single clock. A giant matrix multiply is just broken into many small tiles, each handled by a tensor core in parallel and summed. That one specialization is why a chip today does roughly 1,000 times more inference than one did in 2017. Numbers themselves come in different sizes. A floating point number has three parts: a sign, an exponent for range, and a mantissa for precision. FP32 is the training standard. FP16 is faster but has a narrow range. BF16 is the clever one. It keeps FP32's full exponent so the range stays wide and values don't overflow, but it trims the mantissa. Then FP8 and INT8 for heavily quantized work. Each step down roughly doubles throughput and halves the memory traffic. Quantization maps a model's weights into these low precision formats, shrinking a data center model down to fit on a phone at the cost of a little numerical stability. Here's the truth that governs all of it. The real cost is moving data, not doing math. Memory is a ladder. registers and shared memory inside the SM are the fastest. L2 cache is about 10 times slower. HBM, the main 80 GB memory, is about 100 times slower than registers, and it's the bottleneck. And host RAM over the PCIe link is 1,000 times slower, a last resort. So the entire game is load a piece of data from HBM once, do as much work with it as you can while it sits in the fast levels, and avoid the trip back. All of this is reached through CUDA. Write one line of PyTorch and it falls through a tower of abstraction 20 years deep, framework ops, then libraries like kublas and QDNN, then the runtime and driver, then compiled code, then finally the hardware. And here's why nvidia dominates. The moat isn't the silicon. It's a decade of meticulously optimized libraries, developer habit, and integration with every framework. Competitors can copy the chip. Copying the ecosystem is far harder. In practice, performance is won by feeding big operations, fusing tiny ones, coalescing memory access, and keeping work independent. Then Google pushed specialization further with the TPU, a chip built from scratch for one job. Its heart is the systolic array. Data flows through a physical grid of multiply accumulators. The A matrix enters from the left and flows right. The B matrix enters from the top and flows down. Each cell multiplies the values passing through, adds to a running total, and passes them on. The magic is that a value is loaded once, then walks across the whole array, getting multiplied by everything it meets, with no trips back to memory during the entire computation. Inputs run in BF16 for range. The accumulation runs in FP32 for stability. It's a giant matrix multiply engine wired straight into silicon. One chip is never enough. Two problems: how to wire chips together and how to split the work. Google's TPUs connect into slices, then cubes of 64, then pods of thousands, arranged as a 3D mesh because gradient sharing maps onto it efficiently. And the model is split 4 ways, often at once. Data parallelism gives every chip a full copy and splits the batch. Tensor parallelism splits a single layer's weights across chips. Pipeline parallelism splits the network by depth like an assembly line. And FSDP shards the model so each chip holds less. At the frontier, the interconnect can dominate the compute. So designing the network is half the battle. A few numbers to reason with. An H100 does roughly 1,000 teraflops in BF16, but real workloads hit only 30 to 60% of that because they're waiting on data. Its memory bandwidth is about 3 terabytes a second, and that's often the real limit. The key idea is arithmetic intensity, operations per byte moved. Plot it against performance and you get the roofline. A rising slope where you're memory bound, and a flat ceiling where you're compute bound, meeting at the ridge point. Big matmoles reuse each value so they're compute bound. Element-wise ops and token generation are memory bound, which is why we fuse them. Step back and it's one clean arc. CPUs, universal but only a few cores. GPUs, thousands of parallel cores, a near perfect fit for matrix math. CUDA made them programmable and grew an ecosystem almost as valuable as the hardware. And TPUs, matrix multiplication wired directly into silicon. Thousands of them networked into pods. Every single layer of this stack exists for one purpose: to keep the arithmetic units fed. So when training is mysteriously slow, the answer is almost always memory, interconnect, precision, or too many tiny kernels. Knowing what's down there is the difference between guessing and diagnosing.